So we begin with the problem. We have a, I remember we already talked about this business. We have an x dot, we have a constraint, we have a pure constraint, and we have some terminal constraints. So this is our problem for chapter 4. This is a general enough problem for the rest of the book, and for the deterministic part of the book. This is a mixed constraint. And the special cases of this is ui between 0 and m, or ui between 0 and xit, for example. So that would be special cases of these guys. That one is a special case because we don't put another constraint gut without an x. We include the gut without x constraint into this. This is a special one. Those ones doesn't matter whether x is there or not there, but when u is not there, that becomes special. And we have a constraint of this kind. A special case of that will be, for example, I have a constraint on xit which is bigger than k, or I have a constraint on xit which is equal to k. So those constraints could be more general here. This is a special case of that. And pure constraint xx is bigger than 0. The special case is xi bigger than or equal to 0, xi less than or equal to m. And if that's the case, then h of xi is +1, h of xi is -1 for this, and ht equal to 0 because there's no t here. So h sub t equal to 0. So when we develop the maximum principle, we develop two maximum principles. In some sense, they're equivalent. One is called direct method, one is called indirect method. Most of the book, we follow indirect method. But many people follow direct method, so we should know it. Secondly, the sufficiency conditions are expressed in the direct method. So we're going to express the sufficiency condition in the direct method. We do not have a sufficiency condition in indirect method, but because the indirect method and direct method can be one-to-one, you can go from one to the other. We can easily apply the sufficiency condition to indirect method as well by the transformation that we will talk about later. So the direct is this D, this means direct. And the indirect, I don't put any constraint because most of the book we follow the indirect. So what we don't follow in most of the book, we put a subscript or superscript because we don't always follow that. So it's to distinguish that we put a superscript here. So this is the Hamiltonian. Notice that I'm now going to apply, like in the previous chapter, I did this. Previous chapter, I put a multiplier with the constraint, which is a mixed kind of constraint. But now I have a pure constraint, which was not there in chapter 3. I'm going to put another multiplier to this one directly. That's what I mean by direct. The indirect means I'm going to take the derivative of this and get a u in there, and then apply a multiplier to that part, which if it's order 1, then I will adjoin some multiplier times h1, the first derivative of this guy, with a u term in there. So that's the indirect method. Okay, so that's the difference between direct and indirect. Indirect method, I will use eta. Direct method, I use eta d. And there is a transformation between eta d, lambda d. The mu doesn't change. Mu is the same on both direct and indirect. So there's a transformation between eta and lambda from one to the other. Okay. Necessary condition. Suppose u star is optimal and it gives you x star, which is the trajectory. Then there exists a lambda d, which may be discontinuous at time in boundary interval or at contact time. As we know, we have to allow that. Then multiply function mu, alpha, beta, gamma d, eta d, and a jump parameter zeta d tau. at each time tau where lambda d is discontinuous. That's too many commas. So I'm asking Khusali to remove this comma and this comma. So this reads, and a jump parameter zeta d tau at each time tau where lambda d is discontinuous. Khusali, you got that?
Yes, Professor Sethi.
That comma goes away and that comma goes away.
Okay.
So that is easier to read. It's not incorrect. Either way is okay. But I prefer it to be easier to read in favor of slight insult to the grammar, maybe. Okay. So x dot with a star, that's optimal. It should satisfy this. It should satisfy the constraint. It should satisfy the terminal constraint. It should satisfy the lambda dot d, which is the derivative of the Lagrangian. It should satisfy a condition, which is the terminal condition at t minus. Because remember, things can jump. So we need to make a distinction between t minus and a capital T. So the rest of the problem from 0 up to t is connected by t minus. T can be separate because t is after t minus in some way, okay? Because a jump can happen right here. Right at t, there can be a jump, in which case we have to worry about that. So lambda t minus is given by the salvage value derivatives as usual. This alpha and beta is as before. And this is new. I have a gamma d with the first derivative of the h. Then I have alpha, these are as before, but I have a complementary slackness condition for gamma. Okay. Maximizing condition is as before. This is as before, but now lambda t is discontinuous. And discontinuous is given by at any point tau, which is on a boundary or contact point. Then this is the discontinuous part. Okay, you see lambda minus the plus, and there is some jump here. And you can also see that the Hamiltonian on this side, tau minus, on that side, tau plus. Remember, x is continuous. So tau and a tau minus and tau plus doesn't matter anyway for x, but the u matters, lambda t matters. Okay. And notice if h sub t equal to 0, then Hamiltonian is continuous across that t, tau. You see, if this is 0, so the discontinuity of the Hamiltonian comes only if the constraint itself has a time derivative. If there's no time derivative like this, the non-negativity constraint, you want Hamiltonian to be continuous. These are similar to the previous section, and then we have a complementary slackness conditions. So it's a mouthful. There are a lot of things going on. And what we will do is we will, at some point, we will apply a principle to an example that we already know the solution of, and also solve some other examples. We have a standard, so at t, which is exactly at terminal time t, not at t minus, but t. Well, it has to be this. Because if I give you a little bit of more x, my value has to be s sub x. However, this lambda dt can be different than this lambda dt minus. And if it is different, then there's a jump here, and that jump is given by these jump conditions here. Okay, so that's what I mean by that. This one we always tack on to maximum principle, and I just give this to you. If there is a time t between t1 and t2, which also is a decision variable, then we need a conditions of this kind. This is a similar condition to chapter 3, but similarity only goes as far. But in this particular case, I think they're pretty similar because but there's a gamma here, so that's a difference between the previous chapter and this chapter, and that's because that constraint h. Go here. Problem here. Let's see what's going on here. See that constraint at capital T, right? At capital T, that is almost similar to this constraint. So any multiplier that goes with this one, another multiplier has to go to this one also at capital T, right? So that's what's going on there. So you can sort of see I have a condition beta and a gamma, and that condition is this is with a beta, this with a gamma, this with alpha. Okay. Most of the problems, the jump will happen only at junction times. However, there are cases where discontinuity may happen at a boundary, in the interior of a boundary interval, which may not exceed an average. But this happens when a mixed constraint becomes active. So what they're saying is the following. What they're saying is usually the jumps are either here or here. These are the junction points. But what if the jump is here? Well, it's an unusual case, but it can happen because what happens, suppose this constraint, these other constraints, there could be other constraint, G, X, U, T, that becomes active at some boundary point here. Then you could actually have a jump also here. Okay, so it is, as you can see, things are becoming more complicated if you have problems that are constructed to demonstrate those things. But we are not going to encounter most of the problems that we have. Well, I think there's one problem where this might be happening, but most of the problems that you will encounter will be where the jumps are happening at the junction points. The direct method, so we already have this. So now, if you look at the example 4.2, well, we're not finished with it. Yeah, so we are remark 4. Okay, we already talked about this. Again, we need some matrix rank condition for the problem to be well defined in some way. So I'm usually don't pay attention to this unless you're writing a paper, in which case you have to apply this. But they are straightforward things to apply. Jump conditions. We'll see the jump condition adjoint variable gives us precisely the jump in example 4.2. So we will do the direct maximum principle to example 4.1. So that's called 4.2. And then we will see that we get exactly the same jump. Jump on the Hamiltonian requires that the Hamiltonian is continuous if there is no time derivative on the state constraint, pure state constraint. And this makes intuitive sense because after all, we have a Hamiltonian which gives you the current profit and the value of the future profit multiplied by lambda, right? So the value of the state. And so you would want Hamiltonian to be continuous if there is nothing going on which is outside your influence, which is h sub t. So we apply the direct principle to the example. We apply this 4.13 box to the example 4.1. And it turns out that when you apply all of this, it's just a straightforward getting equations right. And when you do that, you just state all of these conditions. So that is just a statement of the maximum principle for that particular problem. It is, a one by one, you write this down. And then you also write down if lambda d is discontinuous, there's a jump condition. And so you go through all of this. And then once you have written down all of these guys, you already know that this is 0. And this is also 0. So there's no jump at 3 minus a 3. But now you go to 2, 3. And you have to kind of apply, like 2, 3, for example, is this interval. It is not in the boundary. 2, 3 is the interior interval. In the interior interval, all the boundary multiplier will be 0. For example, this is the interior interval, so boundary multiplier will be 0. So one by one, you whittle down these equations. And let me just write down. I think it's a good idea for you to do this on a pen and paper. But interval 2, 3, eta d is 0 for 4.2. And then when eta d is bigger than lambda dot d equal to 0 from 4.9. So you're applying equations one by one in each interval and get the values in different intervals. Okay? And once you are at 2, you go to 1, 2, then 0, 1, so go. So let me just write down. When you do all of that, we will see the adjoint variable lambda dt is actually 1 in this interval and 0 in that interval. This is exactly what we saw in 4.6. So 4.6, we had a derivative of the value function, which is, we know exactly how to compute. We know this is the marginal value. We know this is an optimal solution. All of this is straightforward on this. And now we can see that the Hamiltonian maximum principle we apply gives you exactly a jump, which is this jump in lambda. So that's the only thing I can tell you in terms of building confidence that this crazy, complicated statement of the maximum principle given in 4.13, after all, applies to a simple problem and gives exactly the results that we want. And from there, you take a leap and say, okay, some people have proved this principle for more general problems, and I'm going to use the theory that they have proved to solve my problems. As I mentioned to you, the sufficiency condition apply in the direct formulation, so it is really pretty much the same. I define maximize Hamiltonian, and I get all of those. And if they satisfy necessary condition, if this guy is concave in X, which is also, we had this in chapter 3. And then these other guys are like that. And there's, of course, now H. So H is very similar to A, because A constraint is a bigger than equal to 0. H is a bigger than equal to 0, so very similar. So then we have a theorem of sufficiency, which is very similar to chapter 3. And now it applies to problems with state constraints, pure state constraint. And we also have transversality condition for infinite horizon problem. And this when you t equal to infinity with those transversality condition, the sufficiency condition also goes through for infinite horizon problems. Indirect method. I notice we are assuming order of the constraint to be r equal to 1. So h1 xut is bigger than equal to 0 whenever this is equal to 0. So what we are now saying is the following. I have a pure constraint boundary. I don't bother when this is in interior. That means when this is bigger than 0, I don't need to control x at that time, because I'm in the interior and I will, for the small amount of time in the next interval, I will stay in the interior. So I don't need to apply any constraint. However, if it's on the boundary, then I must say that the derivative of this boundary has to be bigger than equal to 0. So that's the constraint I apply. But the constraint is of the same type as chapter 3. So in some sense, this particular indirect method is more intuitive for us, and it's more related to chapter 3, maximum principle. Because what we're saying is, what if I can apply to this constraint a multiplier, and that multiplier is active only when this is equal to 0? Otherwise, that multiplier is inactive. It is 0. So it's not a multiplier anymore, kind of. So now you see eta. I multiply that to h1. H1 is a similar constraint as G. The only difference is that the mu is applied all the time to this. This one is applied only when this is equal to 0. So that's that idea here. Once you get this idea, we have a maximum principle. And now you can sort of see that if you see eta t is bigger than 0 and eta times h is equal to 0, which means if h is bigger than 0, then eta is equal to 0. So if it's an interior, I don't need this eta. It is 0. But if it's the boundary, then I need a constraint eta t, which is similar to mu t. So mu t also has this complementary slackness condition. But eta t, oh sorry. Now, these are the transformations. The eta d and lambda d are related to eta and lambda this way. So if you give me these, I can find these. If you give me these, I can find these. That means that if I'm using the indirect maximum principle and I get eta and lambda, I can find eta d and lambda d, and I can find the sufficiency condition using the indirect principle. Because indirect principle will require me to use eta d and lambda d. But notice in the indirect principle, in the direct principle, I have this condition. If I have this condition, then you see from here, I have this. So some people put that condition in the maximum principle itself. So when they say eta, they put eta dot less than equal to 0 here. Now, I did that in chapter 3 in a previous edition of the book. But then some of the colleagues of mine in Norway, they said that we don't know whether this is automatically satisfied or it is something. See, here's what happens. If I put more conditions here, it's good for me because this is basically a necessary condition. Necessary conditions give you a set of candidates that are optimal. And if I have more conditions, then I have a less number of candidates, which is better for me. But people are saying that we don't know whether applying eta dot less than 0 gives us less number of candidates, or they don't give us less number of candidates. We don't know that. So according to this guy, I should just leave that in the remark. People can apply if they want to. If they don't apply, that's okay too. So it's left in the remark rather than the maximum principle. To just keeping up with. Okay. So these are just the transformations. I give you how you go from by comparing this and this. If you go the other way, we can go this way. So I can from eta d, I can find eta t and lambda t. Anyway, these are all equations which are straightforward. So I'm just not going to spend too much time on that. Again, the remark 4.3, as I mentioned to you here. So now let's start with examples. And remember, we don't do so much computations in this book. So the idea is to learn the theory and apply it to simple problems that as analytical solution or close to analytical solution, or we can say something about the nature of the solution. But the theory applies to more complicated problems where you have no analytical solution, but you have to go to a numerical solution. Now, I was talking to Ben Susan the other day, and he was, and I know this thing even before, but he was telling me a little bit more about it. He was, before he came here, he was the director of the European Space Agency. And we knew when we learned control theory that the first moon landing was accomplished by an optimal control problem with six state variables. So there are six state variables, position and velocity and all of that stuff. And with the six state variable, they were able to actually land on the moon. But it tells me that more recently, they become more sophisticated, and now they can actually solve problems with 20 state variables. And that, of course, allows them to. I would not be surprised if the Mars landing required 20 variables, because obviously they've done a very good job. Now, you know what? When they solve their optimal control problem with these 20 variables, they approximate, because that's what you can do in numerical solution. But their approximations are pretty good. They actually landed the rover or whatever at exactly the time they're supposed to do. So anyway, it's a miracle. It's a marvelous um, um, achievement. And control theory is the heart of the space program, because everything is dynamics and everything is given by a set of differential equations. And there we go. I suppose there's some delay in the system because they take 13 minutes to get the message there. So you can have a control system with delays. There is a whole theory of maximum principle with system with delays. I don't do that in my book. I used to have some delay in the third edition, but I gave that up. Instead, I gave a reference. So we have now a problem. What's the time now? We got till 3:45, right? Okay.
Yes.
Okay, good. How do you guys see me at the same time, the slides?
Yes, we do.
How come I don't see myself?
Do you see, you should see like a thing on the right side where you'll see yourself.
I don't. Is there a thing that I have to do?
Usually, like when you share the screen, you see yourself on the right side. There's like a little box.
Oh, but I don't see that when I'm on the slides. I see it now. But when
Okay.
I switch to slides, I don't see it.
I mean, you still have the slides on.
No, I cannot see the slides right now.
We can see it.
Yeah, I know. So you see the slides. I see not slides. So I do not know what it means. But anyway, it doesn't matter right now. Next time you do the slides so that I should be able to see myself.
Okay, no problem.
Okay. Okay. And the recording records that, right? Okay, so let's look at this problem. This is the state constraint, pure state constraint. This says use between -1 and +1. That's what it says. These are given as two equations. And it's a very simple problem. So let's see what we do. Now we're solving this problem. The Hamiltonian is given by -x plus lambda u. This is linear in u, so the solution is bang-bang control. And when x equal to 0, we impose this condition, u bigger than 0, so we are not allowed this. So when x equal to 0, the bang-bang control switches to this one. That means control can only take value between 0 and 1, not from -1 to +1. Remember now, I can take value from -1 to +1 in the interior of the constraint, but on the boundary, I need this constraint. Otherwise, x goes negative, right? Because I need to make this guy bigger than 0. And so if I'm a boundary at x equal to 0, I need x dot to be bigger than equal to 0. And x dot is u, so u bigger than equal to 0, so minus is not allowed, so I put this here. So this is the first part that changes. You see, we have already a change from the previous chapter 3. This is what is happening here. The bang-bang have two forms, one on the interior, one on the boundary. We have a Lagrangian. And we have all these other conditions, complementary slackness condition, and okay. As you can see, eta is applicable only when x equal to 0. And now we have delta L delta U, that gives you 0. And now comes a little trick. If you apply lambda 2 dot, lambda dot is 1, lambda 2 minus is gamma, which is bigger than or equal to 0, and gamma x2 is complementary slackness condition. So we don't know, in order for us to solve the problem, we do backward in time. And so we go from lambda 2 and to earlier time. So now we have to go from 2 minus to earlier time, but I don't have a value here. I have some condition here. So what I'm going to do is I'm going to guess. Okay. So we see that, first of all, the optimal control should be one that keeps x star as small as possible, subject to the state constraint 4.35. So this gives you u star, and this gives you x star t. To obtain lambda t, what I'm going to do is we're going to assume that at 2 minus, gamma is 0. So I assume gamma equal to 0. Okay. But it could be also bigger than 0, in which case this will be 0. Okay. So, but whatever gamma is, I can solve the problem in terms of gamma. Okay. So right now I'm going to solve the problem with gamma equal to 0 and see if it works. So now x star t enters the boundary at 0. So now what I have to do is I have to actually go to a picture. Okay. So in order to understand all of these, you need this picture. You can see that x star is going to enter the boundary x equal to 0 at this point 1. Okay. So that's where the boundary is being entered. So what we're now trying to say is the following. Since x star t enters the boundary at t equal to 1, there are no jumps in the interval 1 to 2. And the solution for lambda t then can be obtained from 2 minus all the way to 1 plus. And that solution is easy to do. So lambda t is t minus 2 in this interval. Okay. But lambda t on 1, 2 there's a lambda t. On 1, 2, it is negative. So if it's negative, we have u star t equal to 0 from bang-bang solution. Okay. Now let's see what must happen at t equal to 1. So we know from 4.7, this one, that lambda 1 plus is minus 1. You see, if you put lambda 1 plus, that's 1 here. So 1 minus 2 is minus 1. So we know this is minus 1. I now obtain lambda 1 minus. So I need to find out a jump. And I have two conditions. One is, well, I have one condition, Hamiltonian condition. So I can write the Hamiltonian at 1 plus, and that gives me 1 plus, that gives me minus x star 1 plus lambda 1 plus u star 1 plus. If you can put all those values, you can see. I also can get h1 minus. And this is the same, x is continuous. Lambda 1 as a u star 1 minus now. And because of that, and we know what the control is at 1 minus, the control is exactly x star 1 minus is 0, and control at u1 minus is exactly minus 1. Okay, see, exactly minus 1. At 1 minus, the control is exactly minus 1. Oh, pictures on the other side. See here, here's a 1 minus, and this 1 minus on this side, and the control is this u is minus 1. Okay, so we have gone that far. Once we gone that far, we find the jump. And the jump is given by zeta 1, because there is no ht term here, so this is, we get the jump, we get lambda. And then once I have lambda 1 minus, I can continue go all the way to 0, right? Because we are going from back. So when we start from 2 minus, after 2 minus, we got to 1 plus. Then from 1 plus to 1 minus, we got the Hamiltonian condition to find the jump. So then we got the 1 minus. Once I get a 1 minus, I can go all the way to 0. Because I'm solving lambda t backward. And so I can solve that all the way to 0. So you need to put all of those conditions together. Now lambda t is less than 0, and x star is positive. So can you use 4.39, for example? Let's see what the 4.39 is. You can see bang solution, so we can use that solution, and we have minus 1. We already know that. The time interval, because of the complementary slackness condition, we can easily get this because u star is less than 1, so mu2 equal to 0. And by 4.3, and that's the condition, eta is 0 because x is bigger than 0. Once you have that, then you can get mu1 equal to minus lambda t. And when u star is minus 1, this satisfies 4.1. Let's see what 4.41 is. There you go. So one by one, you have to satisfy all these conditions. And then what happens is, so basically this last paragraph says that when I solve all of these, everything works out with gamma equal to 0. So we have a maximum principle that satisfies gamma equal to 0. If gamma equal to 0 does not satisfy, then we have to start with gamma bigger than 0. And then we have to redo this calculation with gamma bigger than 0. And as you can see, in my book, I always take the guess which is correct, so I don't have to go through this and then and spend 5 more pages to go back to this one. Okay, so that's the idea here. So you can see what's going on. X trajectory goes like this, and then it goes like this. U star is minus 1 here, and is 0 here. But lambda t goes, it was a 2 minus, and it was continuous at 2. It goes like this, then it jumps. And so if you go from this side, it jumps downward at this point 1, and then come to it. So you see lambda is like this. It goes from here, then it goes here. And that's the value at 1, and that's the value at open interval. So if you look at 4.3 is a problem instant in which the state constraint is active at a terminal time right here. In instances where the initial state or the final state are both 0 on the constraint boundary, the maximum principle may degenerate. And then there is no trivial, non-known trivial solution. So some pathological example exists for this kind of stuff, but we don't have any in this book. And then again, there's some uniqueness thing, and there's again a complicated issue. So I just give you the reference. This guy is a friend of mine here, more. Now the sufficiency condition. Well, I have lambda and eta, so I can find out lambda d. So lambda d by the formula that we have gives you this. it's easy to see that H Hamiltonian is given by this, and this Hamiltonian is linear in X, so certainly it's concave. Function gxut is like this. It's again linear in U, and this is X, so it's quasi-linear and hence quasi-concave. And so all I'm saying is you check boxes. You check boxes, and S is 0, so A is 0, B is 0 satisfy the condition of theorem 4.1, which is the sufficiency condition. And so the solution obtained in example 4.3 satisfies all sufficiency conditions, and therefore is optimal. What if I change the problem and I say the problem now goes up to time period 3, and I put a boundary condition that x3 has to be equal to 1? You can sort of see that optimal solution may go like this, then you put u equal to +1, go all the way to 1. You can kind of see that kind of control. So here's a control, and you can you can use the maximum principle to complete all the stuff that is going on, and do all the multipliers. I'm eventually going to go through current value formulation. So first, let's go back to 4.1 and introduce a discount rate where rho is bigger than 0. Turns out that when rho is bigger than 0, the optimal solution will remain the same as figure 1. All we need to do is to calculate the multipliers, and this is done in the next slide. You can write all the conditions you want, and then the red ones are the typos, so that they're all fixed here. And we again have a solution. I just want to give you one thought that when rho is less than 0, this is no longer true. The solution that we just got in example 4.1 is good for rho bigger than 0, but is not good for rho less than 0. It's not a discount rate, but if rho is less than 0, it is still a mathematical problem. And I think there's an exercise in the book, homework, not homework, but there's an exercise in the book where you ask you to solve the problem with rho less than 0. It'll be interesting because it is quite different solution than this. Okay. So the next important point is the correct. This is a difficult chapter. Okay, you just have to go through applying the maximum principle to several simple problems, some of the exercises in the book, to get yourself familiar with applying those conditions and trying to check boxes to find out what's going on. It's basically a laborious task. It's not very interesting and not very edifying as well, but that's what you have to do. So now we have a problem, and now you see the psi here. And now 0 to t, and then there's a salvage value function, which is the function of xt, and then there's a discount factor for this. We have a Hamiltonian, and all we're going to do is to do the current value version of this. And it's more or less the same as before, because now the lambda dot will have a rho lambda in there. So that's one change that's going to happen. So now let's see. We have no difference here, but this is a change here. Okay. There'll be another change in another place where you will see here. You see the rho is coming here. So this is dh dt equal to del dt equal to this plus rho lambda f. So you can write current value formulation, and the maximum principle then is affected in two places. One place is here and one place is here. Or you can do without current value, in which case you will have the standard application, which you can go to previous 4.24 or whatever, and you can apply that box. If the time t to be decided, we have another term here, which is new from previous formulation of this situation. Oh, so the current value version that eta dot less than 0 becomes this. Once again, this is a remark we are not using in the maximum principle. Again, I did not put it here. I did not restrict eta to satisfy this because once again, chances are that it is satisfied when you apply all of these guys. But I haven't seen any paper that does more than what I'm just saying to you. The reference that I'm interested in um, for state constraint, this is my postdoc, and this is a professor at Waterloo, and three of us wrote a very extensive survey of state constraint problem that came in Siam Review. It's one of the top journals in the field. And that is the limit of my knowledge on state constraints. There are a lot of literature that has come since 1995 to now. I'm not following that literature as much as I should, but it's available. But that particular chapter that you have here. This one has more than what we have in chapter 4, and it's written for people who are. It's not serious mathematics because we don't prove things too much here. It's a review paper, so we review the papers in the literature. Questions, because I'm gonna do chapter 5, and this way we can have a shorter session when you do the makeup class, right? So let's do chapter 5. Kushal, you want to load chapter 5, or should I go back and to do it?
I can give it a try. If there's no glitches, I should be able to load it. Let me give it a try.
Okay, try it. I should delete it, right?
Yeah, I mean, if I start sharing, it's gonna show up yours anyways. So
Let's try. I see what happens here.
nope. Okay. Browse.
That's a lot of clicks.
I know. I don't know, something's wrong. It was working earlier, but
Okay, I can just do it myself then.
okay.
Yeah, I can go and do it. So I'm going to go to my website here. That's my website. I'm going to go here in chapter 5. I open that. No, this is pages. I want this one. I want presentation material. Chapter 5. Open. Open is fine, right? Yeah. Now, I just want to tell you, chapter 4 is the most difficult chapter that I covered in this course. And it's also more or less most boring because it's got a lot of things coming to you one after the other. We cannot prove those things, but there are lots of these equations, a lot of boxes that need to be checked in solving any problem. But now, starting chapter 5, we sink our teeth into some problems that have some meaning for us. I'm not saying that the problem that I do in this book are the state-of-the-art finance problems that you will be able to use them into making money in the stock market. In any way, the stock market is going crazy anyway. Nobody knows what's happening with this GameStop. But regardless, I'm going to start with the finance chapter, partly because the finance chapter is easier than in the production chapter. I wanted the production chapter to be the first one, but production chapter is slightly more complicated. So my theory is always that you start from simple to more complicated and not the other way around. The math people like to do complicated and then do special cases. My own view is to go from simple and build to more complicated cases. That way you have a time to absorb and learn. So, chapter 5 has two problems.
We do not see the slides, Professor.
Huh?
You'll have to do share screen. We don't see your slides.
Oh, I go back to share screen. Here, just a second. Share screen. And then go to chapter 5. Got it?
Yes, we see it now.
Okay. So what I'm saying is that we have two problems that we deal with. One is a simple cash balance problem that I wrote as part of my thesis. And the other one is a problem that was existing in the literature, but the authors did not know what to do. They made mistakes. It was in a prestigious journal called JFQA, Journal of Financial and Quantitative Analysis. When I looked at the problem, I said, these guys don't know control theory. So I rewrote the paper. And it's quite different because the solution was wrong. And then when I sent that paper to the journal, I told them not to send it to at least one other than the author of the previous paper. When I get a review, they only send it to the author of the previous paper, and the guy rejected the paper. And I wrote to the editor that the guy, whoever, because I cannot say it is the author because it's blind for me. So I wrote to the editor. I said that whoever reviewed this paper has no clue of control theory, has no idea. So please send it to somebody who knows control theory. And they did, and the paper was accepted. And then it was published also in JFQA. Many years later, I wrote that I met this author, but we didn't talk about it. Anyway, that's my little story for this. That will come when we do optimal financing or corporation, finite horizon, then we'll do infinite horizon. Then there's a numerical example. And then this problem that we do here will become more sophisticated when we do chapter 12, when we do a consumption investment problem and we have a stochastic control. So this is no longer the state of the art. It's a deterministic problem, and a finance had a deterministic problem in the earlier literature when people did not know how to deal with stochastic problems. So they limit themselves to deterministic problems. And only much later that the finance became stochastic, because economics was also very deterministic for a long, long time. And many economics is still deterministic. But anyway, that's... So the cash balance problem is like an inventory problem. And in the simplest form, it says I control the level of cash to meet the demand for cash at a minimum total cost. If I keep too much cash, then it loses money because I can invest this money and earn more. So there's an opportunity cost of keeping too much cash. Okay. So I have cash and I can put money in bonds, which earn higher return than cash. On the other hand, if the cash balance is too small, then I have to sell securities many times to meet the cash demand and incur broker's commission every time I do that. So the trade-off is between cash and the security balance. Given a demand, how much money I should keep in cash and security balance. Okay, it's a very simple problem, and that was published in JFQA. JFQA started the journal at that year. I think that this may be one of the first paper published in that journal. And then, of course, this other paper came later in the same journal. It's one of the finance journal that is in UTD 24. Okay. So T is the time horizon. XT is the cash balance in dollars. YT is the security balance in dollars. It's really a very simple problem, and it has an analytical solution, and it gives you some idea of, using control theory in a very simple setting. And it got published only because the control theory was new at the time. People did not know much about it, and the finance people knew nothing about it. So a top journal in finance publishes a paper, which is right now will not be published because it is a very simple problem. But it was many years ago. So DT is the instantaneous rate of demand for cash, and that's a forecast. I have to have I'm doing business, and I know when I have to pay and when I get money. This can be positive and negative. When the money comes, it's negative. When money goes out, it's positive. UT is the rate of sale of securities in dollars, and a negative sell rate means a purchase. So when I sell, it's positive, when I purchase, negative. Alpha is the broker's commission between 0 and 1, strictly between 0 and 1. R1T is the interest rate earned in the cash balance. I keep my cash balance in a savings account, and that gives me interest R1T, which I predict to be this over time. It's just to make it more complicated control problem, because usually you don't always know what the rate would be forever. You have to be some stochastic stuff in there. R2T is the interest rate earned on security balance, which is a bond in this case. So you can see the rate of change of cash. First of all, I'm earning interest on this balance. That's R1 times X. Then remember there's a T here. So you don't put T in control theory when it's understood. So this is the cash going out. It's continuous time, so the demand has to be a rate. So the rate at which the cash is going out is minus D. When I sell securities, I get that money. So my cash increases. And when I get that money, I have to pay the broker's commission. When I buy securities, which is negative, then I lose cash. But then I still pay the commission. And I already gave you in chapter 4 how to deal with this absolute value. You change it to U1 and U2, and you call this to be, you call this to be U1 minus U2 and call this to be U1 plus U2. And I have initial cash balance. So this is how you write a state equation. Well, Y dot is the bond balance. It earns interest, so the bond value keeps going up at this rate. And when I sell bond, my balance of the bond goes down by this rate. But I don't pay my commission comes out of cash regardless. And I have initial value of the bond, initial balance of bond at Y0. I cannot sell at a very high rate and buy at a very low rate, a very high rate. So I put limit on the rate at which I can buy these securities. Once again, I do that to make the problem so that we can apply the maximum principle. Remember, if one of them is infinity, then you can have an impulse control. That means you can sell all at once at one instant. And I had a section on that in the book, but I kind of removed it. And objective function, there are many ways you can write it. But one simple way to say is that I am doing pretty good if my end wealth is as large as possible. Because in the end, I will have xt and yt. So if I can maximize this, then whatever I'm doing is I'm doing good. You can also calculate the income and expenses and take a derivative. But you know what? That will give you the Boltzmann form. This is the Meyer form. So we can write the equation in Meyer form or Boltzmann form, but we write in Meyer form, and Meyer form is xt plus yt. Hamiltonian is lambda 1 times this equation and lambda 2 times this equation. And lambda 1 dot is the derivative of this. We are using standard maximum principle. And lambda 1 t equal to 1, lambda 2 t equal to 1, because xt plus yt is linear, so the derivative of these is 1 and 1. So I get these. But if I get these, I can solve them right away. So it's a very simple problem because I can solve for lambda 1 and lambda 2 right away, because it does not involve x. So it is a very simple problem, and I solve it that way. You can see the lambda 1 t is exactly the future value of a dollar. So if I have a dollar in savings account, then that dollar will grow at this rate, but this rate is changing, so I have to put integral. So at the capital T, that dollar will become this value. So the lambda 1 t actually gives me that value. That should be the right value of my dollar right now, because my value of dollar right now is really this, because it's going to, in terms of objective function. Remember, lambda 1 t is a margin value in terms of the objective function. So in terms of objective function, the value of $1 at small t, it will add that much to this xt. Similarly, if I have $1 in bond, and if I just keep it in bond and do nothing with it, then it will give me yt, this much amount to my bond balance for $1. If it's $5, it'll be 5 times that. So this is so now what we're doing is we apply the maximum principle, we can now see the meaning of many things. So lambda 1 is no longer an adjoint variable. It has an adjoint variable with a meaning which we can easily sink our teeth into, right? So we can exactly see what is going on, okay? So that is, and it's coming from maximum principle. We didn't do this. We took the derivative of the Hamiltonian with respect to x and solved this differential equation to get here. But when we get here, we can see what it is, and it makes sense. We already talked about this. And we know that we don't need to put this. So once we have that, we rewrite the problem in terms of u1 and u2, and there are two control variables now. And one of them is at this constraint, and now that has this constraint. So we can transform this constraint into this constraint. Then I write the Hamiltonian. And so in Hamiltonian, I put u1 minus u2 here, u1 plus u2 there, and then I take the terms in u1 and terms in u2, because I need to maximize the Hamiltonian with respect to u1 and u2. So you can see that when I take the terms in u1 and u2, I have a w1, this is the u1 u2 part of the Hamiltonian. So I can easily maximize this Hamiltonian. This is bang-bang control for U1, bang-bang control for U2. You can see U1 star is a bang between 0, U1, and this. If this guy is positive, I buy at the maximum rate. Is it? Yeah. If this is positive, okay. So what we are doing is we are selling. So selling is positive. and buying is negative, right? So if this is the case, then I sell as much as possible. If this is bigger than 0, if this is less than 0, I don't sell. Similarly, bond, I sell as much as possible if this is bigger than 0. If not, now you see we want to find the meaning of this guy. And now let's see why this is optimal. It's easy to see why this is optimal. U and T represent the sale of securities. 5.16, which is this one, says that if this is bigger than 0, I sell as much as possible. Right? Look what happens. If I keep the money in cash, its value is lambda 1. If I keep the money in bond, its value is lambda 2. Right? Now, if I sell, I get, so let's just go here. Sell at the maximum allowable rate if the future value of $1 less the broker's commission. So this is the future value of $1. And when you multiply by 1 minus alpha, this is the future value less the broker's commission. If the future value of $1 less than broker's commission, okay, is bigger than lambda 2, then do not sell the securities. If the future dollar less the broker's commission is greater than that, then do not sell the securities. In case the future value of dollar less the commission exactly equal to the future value of dollar, then it's a singular control and I can do whatever I want at that point. Similarly, U2 represent the purchase of securities. Here we buy, do not buy, or are indifferent. If the future value of $1 plus the commission rate is less than, greater than, or equal to the future value of $1 worth of securities. So you can sort of see here, it is similar to the thing here, but you can see what's going on. It says here, if the future value of $1 plus the commission is less than the future value of the equivalent worth of securities, then I buy. Because my future value sitting in dollar is less than the amount of securities I get from that even after paying the commission. So these guys makes total sense. Okay? And this is just saying it is simple to it's common sense that you would not sell and buy at the same time, but mathematically you can show that when I follow this policy, then this one will be automatically satisfied. So when I sell this policy, you can sort of see that if U1T is bigger than 0, then U2T has to be equal to 0. So you can say that if this one is this, which means I have to sell, then I will not buy. That condition says don't buy. So U2T equal to 0. So if you look at this picture, lambda 2, 0 and lambda 1, 0 is some value here, which we know, and it is going to end at 1, 1. So time is going from here to here. But lambda 1 and lambda 2 are functions of time. And this function depends on these guys, R1 and R2. So depending on the trajectory of R1 and R2, one can say that my trajectory of lambda 1, lambda 2 in this lambda 1, lambda 2 space will go like this. And eventually end to 1. If it goes like this, then for that problem, okay, if I'm in these two intervals, I keep the present portfolio. That means I do neither buy nor sell. if I am here, I buy security at the maximum rate because the value of lambda 2 is higher than value of that times lambda 1. Okay, the greater than is on this side. Similarly, if I'm on this side of this line, I sell security at the maximum rate. So I sell, then I do nothing, then I buy, then I do nothing, then I buy, and then I do nothing at the end. So this is the solution of the problem for that R1t, R2t, for which this is the trajectory. You can write this in a different space. You can divide the lambda 1 by lambda 2 because you can actually write this equation in terms of lambda 1 divided by lambda 2. So if I can divide by lambda 2, lambda 1, then you can sort of see the same graph that I wrote can be written this way. So here I sell, then I keep, then I buy, then I keep, then I buy, then I keep. This is time. These are the time intervals. This one doesn't have the time intervals. This implicitly allow you to find the time when you have lambda 1 divided by lambda 2. You can tell what time it is. But on this graph, we can take this and you can actually write the time space here because we have only, I'm writing two-dimensional figures. If you wrote three-dimensional figure, you can do lambda 1, lambda 2, and time, and the time on this scale. Then you get a three-dimensional figure, you can do a better job, but it's difficult to see. Any question? Because this is a very simple problem. And it gives you some idea of what the Maxwell principle does. This is a also simple problem, but obviously somebody made mistakes. So let's see how far we can go on this one. In this model, what happens is that a company wants to maximize its value to the stockholders. That's the value of the company. Okay. And the company at any given time has the assets. This is the assets of YT. And XT is the current earning rate in dollars per unit time at T. So what company is interested in is kind of dividend policy. It wants to pay dividend out of earnings. So that's one way you can give money to the stockholders. Or it can keep the dividend, don't give the dividend, but invest that earning, which will give you future dividend in a larger amount. So the idea now is, what is the financing policies of this company? Between new equity financing. So there's one more, there is a, so when I keep a fraction of current earnings, this is the, if this is the fraction of the retained earnings, then 1 minus VT is the fraction of the dividend payout. Whatever I don't invest, I pay out as a dividend. So this is one way the company can finance itself. The other way the company finances itself is to issue new shares. That's called a new equity financing, and it issues new shares that bring in new stockholders. Okay? But when you issue new shares, you have to go to an investment broker, and they charge you some money for issuing new shares. We call them flotation cost. And we assume that the flotation cost, which is the transaction cost for external equity, okay? And so 1 minus C is the flotation cost. So what I get is the C. You could put C here and 1 minus C here, but this is how the Krauss and Lee, the paper that I'm describing was formulated by Krauss and Lee. Those are the people that I told you didn't know control theory, so they botched the problem. One was a professor at UCLA at the time. Okay. So rho is the discount rate, which is also similar to what the stockholders require. It is called the cost of capital. It is the stockholders' required rate of return. How many people have not taken a course in finance? Anyone who has not taken a finance course at our school?
I haven't.
Oh, you haven't. You will next time, right? Okay. Okay. Well, you this sometimes it may be better to take this course in the second year, but I think now what's happening is everybody's taking in the first year, which is okay. These are simple to understand, and when you go into take a finance course, then you will remember what I'm telling you, and maybe you can ask more questions, because I can tell you that even some finance people are sometimes not completely clear what's going on, at least academic. Let's put it this way. So we have a continuous discount rate. R is the actual rate of return. Clearly, the company doesn't have to be in a business if R is not bigger than rho. Because if R is less than rho, then I'm earning less than what stockholders want. So this company should just fold immediately, go out of business. The planning horizon is either finite or infinity. So we will solve the problem both ways. So a lot of emphasis on formulating the problem. Okay? Okay, once you formulate the problem, then the next is applying the maximum principle and do the solution. But what we want to learn in research is how to formulate the problem, and then also formulate the problem that's reasonable, but at the same time solvable. Okay, because if you formulate the problem which is not solvable, it doesn't do much good. So there is a trade-off here. The current earning, I'm not going to finish this model, but we can do that later. The current earnings rate is R times Y, which is equal to X. Because we earn R on the capital invested, so R times Y, and so that X is the rate. The reason I do that is because Krauss and Lee formulate this. They are now saying that I cannot just grow the company any way I want. Okay, there's a bound on how I can grow. So first of all, write the equation. X dot is just R Y dot, and we already know what Y dot is. Y dot is R times Cu plus V times X. Okay, so that's R. What is Y dot? Y dot is the rate at which the bond balance is increasing. Well, the bond balance increase. Remember, this U are in terms of fraction of the earnings rate. You see this U? X is a multiple of the current earnings, fraction of the current earnings. So this is not absolute value. It is so what is being financed is UT times X. What is being retained is VT times X. So U times X, V times X. But if I sell the securities, okay, if I sell the securities, I need to only get, if I put that much money, I only get CU, right? It is notice here because I have to give 1 minus C to the brokers. So I'll only get C times U. U times X is the dollar amount, I get only C times. So that's Y dot. And I multiply by R, so I get X dot equal to RY dot. Why am I doing this? Because this is the rate at which the company is growing. And Krauss and Lee wants to put a constraint on the rate at which the company is growing. Okay. Well, So the upper bound rate of growth implies the following constraint. So y dot divided by y. This is the rate at which the bond is growing, and if you divide by y, this is the rate of growth because you divide by y. And by this formula, we get y dot y equal to this, and they want this to be upper bound by g. What is the reason? Well, one reason is that if the company is growing if the company is very profitable, it will result in impulse control, because you will take any money that comes to you, because the stockholders are very happy. R is bigger than rho. The second reason is that if you grow at a certain rate which is much higher than G, then you are not getting into good investments. So think about it. If you are in a business of drilling for oil, then I can drill the oil, but sooner or later, if I drill too much, put too much money in drilling, at the rate at which it's too much, then I may be going to oil wells that are not as productive. I may find places that are not as good in oil down in the ground. And so basically what is going on in finance is that when you invest money, first you invest in the highest possible investment, then you go to the next one, then you go to the next one, until your R is equal to rho. Because as long as R is bigger than rho, you can keep investing. So you can put an upper bound on G that kills you this kind of idea that you cannot find good opportunities to invest at that rate. If you do more than G, you cannot do that, cannot sustain it. Later on, much later on, my friend Taxer and I rewrote this paper. Not rewrote, we generalized this paper to stochastic problems. And that came out in one of the very distinguished journals called Mathematical Finance. But we are not going to cover that. The last thing that I want to say is that in the formulation is, what is the objective function? Well, the objective function is kind of interesting. It says that the firm maximizes its value, and its value is given as the present value of the future dividend accruing to the share outstanding at time zero. So if I hold a share, I'm going to get a dividend 1 minus V times X. And if I discount that dividend at this rate, which is my required rate of return, then my share had that value. But remember, this is the total dividend issued by it. So that will be issued to all the shares. So the company's value is the value of each share times the number of shares, which means the company's value to the set of stockholders who own the company. Okay, so that is the value of what is called the future dividend stream outstanding at time zero. But what happens is that those are initial stockholders. And sometime later, I'm also issue new equity. So I'm bringing new equity. So if I'm bringing new equity, those become owners of the company, not at time zero, but some other time t. And at different time t, different owners come into the company. Remember, owner means share. If I sell a share to another person, the share is the owner of the company. That share goes to another person, then that person owns the company. We don't have to worry about person per se. We only worry about the number of shares wherever they are kept. Okay. So what happens? Well, a portion of this dividend is over time also going to the new stockholders. Remember, at time zero, I want to maximize the value of the firm to the initial stockholders at time 0. Okay. And so if you take this value, it is some of the dividend also going to people who came into the company's ownership between 0 and T. Because remember, company is also issuing external equity. So here's a trick. By the way, Krauss and Lee made mistake in deriving this formula. And I'll talk about this a little bit later. So what happens is this. In an efficient market, the dividend go to the new equity. But in an efficient market, they're not going to get any more than the row. Because there's no reason for the original stockholders to give them any more than what they want. Why should they give them more than row if all they want is row? That means that if I bring in this much money and its discounted value is that much, then that's the money they will get. The dividend going to them cannot exceed this, because if it exceeds this, it will give them more than row. So I subtract this guy from this guy, and the value of the company then becomes this. There's another way to look at this. There are many ways to look at it. And you may not learn every one of those in finance course, but I have my own view here. One is the net present value of the total future dividend accrued to the initial share is the difference of these two expressions. The intuitive explanation is this. One of the intuitive explanations is this. That the value J to the firm is the present value of cash flows going out from the firm to the society minus the money coming from the society to the firm. So if you think about what is the value of the firm to the society, it is exactly what the society gets from the company minus what the company gets from the society, which is exactly this. So there's another way to look at it. This is one way to look at it, efficient market. There's another way to look at it. And there's a third way to look at it. That is, there is a paper is written by Millen and Modigliani, who won the Nobel Prize for their work on this problem. And they showed that this approach is what is called a cash flow approach. But there is also a dividend approach. That means the dividend approach is the following approach. I can actually find out by calculation as to the dividend earned by the initial stockholder, one share, one at the beginning at time 0. So what I do is I find the dividend at time 0. Then at time dt, I find the dividend, but I find out which one goes to this guy and which one goes to not this guy. And then I take the present value of the dividend that accrued to that share. For that, I need to find out the new stockholders coming into play, and I have to apportion the share value to these guys. Miller-Modigliani argued that the dividend approach is equivalent to this approach. And Krauss and Lee did not have a good proof of it, so I rewrote the proof. And when I rewrote the proof, I actually ended up learning more on Miller-Modigliani. Then I decided the Miller-Modigliani also needed some revision. So I wrote 3 or 4 papers on extending the Miller-Modigliani to get to this formula of the value of the firm. So I'm going to close this. We're going to solve this problem now. We're going to solve the problem of maximizing this value objective, which is coming from here, by using the control u and v with the differential equation given by this, and the control constraints u bigger than 0. Certainly, I don't want to. This is what, if this is the case, Miller-Modigliani's paper goes through. But people can instead of equity, they can retire the equity. That means I can actually buy back the shares. When I buy back the share, this is negative. And when this is negative, Miller-Modigliani needs much more sophisticated proof to prove this, and they don't have it in their paper. Okay, so there are papers listed in this, and if you're curious, you can go to them. And of course, earnings, I can only give a fraction of earning, and the rest goes to dividends, so they have to be between 0 and 1. Finally, there's a growth rate constraint because we have, so there are 3 mixed constraints. These are actually just the control constraints, and we have to solve this problem with those constraints. Okay, that's our job next week, next Monday, right? I think that if you have other questions on Monday, let me know, and we will continue to do that. So Monday is a class, Thursday is a class, and then there's an exam, right?
Right, Professor.
Okay. So Monday class is now settled from 1 to 3:45.
Correct.
I have a question now. Who is the person who is not going to be able to make the class, and what time he cannot make the class? For the entire time? Is the entire time you cannot make the class? Let me
I
get
think it's
to.
Yi Hong.
Yeah, it's me.
Or you cannot make the class entire time, right?
Yeah.
Okay. So then we'll do 1 to 3:45, and we may finish early, or we may continue on, and then we may finish early on Thursday, because the Thursday, well, I just continue, even though the exam will be from Kushali. The exam is going to be from chapter 1 to 6, right?
Right, chapter 1 through 5, and then 6, whatever we cover until next Thursday.
We'll cover 6.
Okay.
Yeah, we'll cover 5 and then 6. Yeah, 5 is half covered. I mean, so we can cover 6. The thing is that towards the very end, if we have material, we can also discuss some new papers that are not in the book. But anyway, if you slow me down, then we cannot finish the book. If I go at this rate, maybe I'll finish the book and maybe do more things. So
Need to assign the homework before they leave. So I think I'll already send it out in advance, but I'll still repeat it. It's 4.9, 4.14, and 5.10. I already sent it out. I'll send out an email again. It's due on Thursday. There'll be another homework assigned on Monday that's also due on Thursday. So you'll have 6 problems due on Thursday. And Minman's going to have his TA sessions on Tuesday and office hours on Wednesday.
Kushali, let's try to decide on the homework for Monday tomorrow if we can.
Okay.
Then send it to these people, our
No
students. And then they have all 6 problems to do on Thursday, so they have a little bit more flexibility in how they assign their time to do the problems.
Okay.
Okay?
All right. See you all on Monday at 1 o'clock.
Okay, I survived.